So now we're going to look at the actual question in the exam. So far I've given you a little background on why we ended up with this normalization. And in the question, the first thing we ask is, what is Dmin? What is the minimal distance? And the second thing we ask is, what is the probability of error? So to do that, we look at the cheat sheet. And the cheat sheet, we pick out a couple of equations that are going to help us respond to this question. First of all, what is Dmin? Dmin is just the minimum distance over, all pairs of points. So if I were going to take all the different points in the constellation, calculate the distance between all of the different possible pairs, whichever one was the smallest, that would be the minimal distance. And of course, this is a very important parameter because it is the minimum distance that dominates the probability of error calculation. So here we have what we call the union bound approximation, and this is given by 2 times k, where k is the number of pairs of symbols at this minimum separation, divided by m, the number of points in the constellation. And then we have the q factor, or the q function, which is the integral of the Gaussian probability density. And here we see Dmin entering prominently. So in the true exact probability of error, there would be other terms for pairs at different distances, but the dominant term, the one that really determines the probability of error, is that minimal distance. So when I'm looking at what is a good constellation, what really makes a good constellation is having a big minimal distance, that the smallest distance, which will dominate performance, is as big as we can get it. And so this exercise is all about trying to say, is this a good constellation? When I pick these 16 points and I scatter them this way, is this a good way? And how am I going to know? Well, one way I can focus on it is by finding this minimal distance. And once I have the minimal distance, of course, then I can put it in this equation and actually get the probability of error. So the first thing we have to do is look at these different pairs and these different distances and find out which one is the smallest. So we have to look at our geometry here now and find out. So there are a couple candidates that come to mind. There is certainly this distance here, let's say, between these two inner points. There are 4 inner points. There's some distance in between these. Looks kind of small, this distance. Maybe that's a minimal distance. So that's one I'm going to be interested in. What else might be in a minimal distance? Well, another minimal distance could be, let me see, here to here. Let's put that as a possibility as a minimal distance. And another really tricky one looks here. So by eye, I can't really tell which of these 2 distances is greater. And so I'm going to have to do some math to figure out which one of those is bigger. Some things I can see are the same. First of all, what is this distance? Well, this coordinate is at minus the square root of 2 ES over 27. This is plus. So this length here is kind of simple. It's 2 times the square root of 2 ES over 27. Now here, this distance is 0, and then I have 3, so this distance is 3 the square root of 2 ES over 27. And now what is the length here? Well, that's a little trickier. I'm going to pull that off to the side, look at some geometry, and figure out what that length is. So first of all, this coordinate is minus 2 ES the square root of 27. This is 3 times the square root of 2 ES over 27. So the length here on this bottom is 2 the square root of 2 ES over 27. And this height here is the square root of 2 ES over 27. So of course, if I want to know the length of hypotenuse, I know that it would just be the square root of the squares of the 2 sides. And so I get here 2 ES over 27 plus 4 times 2 ES over 27, all square root. So I get, let's say, the square root of 5 times the square root of 2 ES over 27. Okay, so now I can say this is the square root of 5 times the square root of 2ES over 27. So now I have three lengths that I'm considering, and I want to know which of those three is the minimum length. So first thing I do is I compare 3, square root of 2ES over 27, versus 2. Well, clearly 3 is greater than 2, so I'm not going to consider this. This for sure, not the minimum distance. And the square root of 5, well, it's certainly bigger than the square root of 4, which is equal to 2. So I know that the this distance also is not the minimum distance. So that leaves me with a clear choice that Dmin is equal to 2 times the square root of 2ES over 27. From this choice, I can also find, if I like, the normalized Dmin. So capital Dmin is in terms of ES, and if I put lowercase Dmin, I will be normalizing that. And to do that, I'm going to use the relationship that EB times log 2m equal ES. So in this case, m is equal to 16, so 4EB is equal to ES. So I take the average energy per bit. There are 4 bits in a symbol, so the energy of a symbol is 4 times EB. And so that means that if I were looking at Dmin, which is equal to Dmin uppercase, divided by the square root of 2EB, then I would get 2, the square root of 2ES, divided by 27, times 1 over the square root of 2EB. And of course, ES I can put in, that's 4EB times 2 divided by 27 times 2 times EB. And of course, the 2's and the EB's cancel out. The 4 I can bring out, and that becomes 4, the square root of, 1 over 27, or 4 over the square root of 27. So now the last point would be to use this equation here for the probability of error, and we just have to plug and play. And what are we missing? We've found the Dmin. We know m, that's 16. The only thing that we have left to do is to find k. And what is k? K is the number of constellation pairs of points that are at the minimal distance. So now we really have to go back to our constellation in order to determine what k is. Let me get some of these notations out. This was not the minimum distance. We don't need that. So now we have the minimum distance is this 2 times the square root. So between, here is 1 times the square root, and here is 2 times. So the distance between these two, distance between these 2 points are clearly at the minimum separation. These, of course, we have 4 pairs here, which are at that minimum separation, and then 4 total here. And of course, the others are at a greater separation. So that brings us to the calculation that k is equal to 8. And we can write an equation now for the total probability of error. And so we have the probability of error is equal to 2 times k, which is 8, divided by m, which is 16, the q function, and we need Dmin, which is 4 over the square root of 27, and that is multiplied by the square root of EB over N0. And so now, of course, we could simplify that. We have 16 divided by 16, so it's just Q of the Dmin times EB over N0.